That skipped breakfast isn't just emptying your stomach, it is forcing your heart cells to choose between eating themselves alive via microscopic autophagy or triggering a sudden, silent electrical short circuit. Intermittent fasting has surged to global dominance as the ultimate metabolic panacea, celebrated for its rapid reduction of adipose tissue and profound reset of systemic insulin sensitivity. Yet, while your waistline shrinks and your cognitive clarity peaks, a polarizing, high-stakes medical debate is unfolding within the clinical cardiology community. What is fasting actually doing to the human cardiovascular architecture? Is this periods of strategic food deprivation a therapeutic masterpiece that rejuvenates your blood vessels, or is it a silent cardiac stressor pushing your myocardium towards structural strain? The physiological truth is far more complex than any popular diet trend suggests. When you deprive your system of exogenous nutrients, your heart is forced to fundamentally alter its cellular energetics. It shifts from its preferred fuel sources to rely heavily on lipid-derived compounds, a transition that triggers profound changes in myocardial elasticity, vascular endothelial health, and autonomic nervous system regulation. For some individuals, this shift lowers systemic inflammation, stabilizes arterial plaque, and decreases hydrostatic blood pressure. For others, the sudden hormonal spikes of cortisol and adrenaline, combined with acute shifts in vital serum electrolytes, can cause dangerous myocardial remodeling and trigger lethal electrical arrhythmias. This extensive, medically rigorous script completely deconstructs the cardiovascular reality of intermittent fasting. We will dissect the microscopic changes occurring within cardiomyocytes, the biochemical pathways of cardiovascular autophagy, the physics of endothelial shear stress, and the clinical realities of long-term cardiac adaptation. Let us look directly at the science. When you choose to restrict your food intake for an extended period, your heart cannot simply take a break or reduce its workload to match your empty stomach. It is an unceasing mechanical pump that must contract every single second of your life, requiring a massive and steady supply of cellular energy known as adenosine triphosphate, or ATP. Under standard dietary conditions, your heart functions as an incredibly adaptable engine, burning whatever fuel is most abundant in your bloodstream. When you eat a diet rich in carbohydrates, your digestive tract floods your system with glucose, and your pancreas releases a large amount of the hormone insulin. In this environment, your heart cells readily absorb this glucose alongside passing fats, using them to power the continuous contractions that keep blood flowing to your organs. However, when you enter a fasting state that extends past 12 to 16 hours, your body's internal energy supply lines undergo a drastic reorganization. Your liver completely runs out of its stored carbohydrates, insulin levels drop to their absolute lowest baseline, and your body enters a state of survival. To keep you alive, your system begins to aggressively break down fat tissue, releasing a massive wave of free fatty acids into your bloodstream. Simultaneously, your liver begins converting these fatty acids into tiny, highly efficient, water-soluble molecules called ketone bodies, with the primary star being a molecule named beta-hydroxybutyrate. Faced with this sudden shift in your blood chemistry, your heart muscle must pull off a rapid and profound energetic pivot. It stops looking for glucose and upregulates specialized transporter proteins on the surface of its cells to capture the passing wave of free fatty acids and ketones. Once inside the heart cells, these fat-derived fuels are routed directly into the microscopic powerhouses known as the mitochondria. Here, they undergo a systematic dismantling process that chops the molecules down to release their stored chemical energy, packing your cellular batteries with ATP. From a clinical and thermodynamic standpoint, running the heart on these newly created ketone bodies is an exceptionally efficient process. Ketone bodies are often described by cardiologists as a premium, clean-burning fuel for the myocardium. When your heart burns ketones instead of simple sugars, it actually generates more energy per unit of oxygen consumed. This occurs because the chemical processing of ketones optimizes the internal electrical gradients across the mitochondrial membranes, allowing the heart to generate robust mechanical work while demanding less overall oxygen. For a healthy individual, This transition into ketosis acts like a metabolic rest for the heart, reducing oxidative waste molecules called free radicals and allowing the cardiac muscle to perform its continuous mechanical duties with maximum efficiency. However, this metabolic switch is a double-edged sword that can introduce serious clinical perils if an individual possesses an underlying subclinical cardiovascular condition. In a perfectly healthy heart, moving back and forth between burning sugar and burning fat is a harmless and natural display of metabolic flexibility. But if a heart has already been structurally compromised, such as by chronic high blood pressure, early-stage heart failure, or narrowed coronary arteries, its internal mitochondria are often structurally damaged and have lost this vital flexibility. When a compromised heart is subjected to a sudden, unmanaged fast, the massive and uninhibited torrent of free fatty acids released from your fat tissues can completely overwhelm its broken mitochondrial machinery. Because these damaged powerhouses cannot burn the incoming fat fast enough, a dangerous buildup of partially processed lipid intermediates, such as ceramides and diacylglycerols, accumulates directly inside the heart muscle cells. This state is clinically known as lipotoxicity. These toxic fat accumulations act as potent stressors, causing the mitochondria to leak immense amounts of damaging free radicals and severely disrupting how the heart cells handle calcium. Because calcium is the exact chemical trigger that controls how your heart muscle fibers tighten and relax, this disruption directly impairs the heart's ability to pump smoothly. The heart can suffer from localized stunning, making it significantly more vulnerable to injury or low oxygen states. This reveals a critical medical truth. While a healthy heart thrives and thanks you for the clean efficiency of fasting, induced ketones, an already struggling heart may cry out under the acute structural strain of a massive, unmitigated fat overload. As your extended fast progresses past the initial fuel transition, the continuous absence of incoming food triggers a deeper and more profound structural response within your cardiac cells. This response is governed by your body's internal nutrient sensors, which constantly monitor your blood for the presence of proteins, sugars, and hormones. Under standard dietary conditions, the regular consumption of food keeps a master protein complex inside your cells, known as mTOR, highly activated. When mTOR is turned on, it acts like a green light for cellular growth and replication, ordering your heart cells to constantly build new proteins and expand their size. When you enter a prolonged fast, the complete collapse of circulating insulin and the total absence of amino acids from dietary protein cause mTOR to completely turn off. Simultaneously, as your immediate cellular energy levels decline, a sensitive internal fuel gauge called AMPK becomes highly active. AMPK functions as the direct antagonist to mTOR. It steps in, shuts down the cellular growth machinery, and shifts your heart cells out of replication mode and into a state of intense, deep internal maintenance. This shift activates a vital survival mechanism known to medical science as macroautophagy, or cellular self-eating. Because the muscle cells of your heart are post-mitotic, meaning they do not readily divide, multiply, or replace themselves throughout your entire lifespan, they are highly susceptible to the gradual accumulation of internal wear and tear. Over decades of constant beating, the structural proteins inside your heart can become warped and misfolded, and the internal mitochondria can become old and senescent, leaking toxic waste into the cell fluid. Fasting-induced autophagy provides an automated, highly organized cleanup crew to solve this issue. Once activated by AMPK, a tiny membrane forms inside the heart cell, expanding to selectively gather up this internal garbage. It wraps itself tightly around the damaged proteins and the worn-out powerhouses, creating a sealed vesicle that is then fused with an acidic internal incinerator called a lysosome. The powerful enzymes inside the lysosome completely dismantle this cellular waste, breaking it down into raw, pristine amino acids. The heart cell then takes these recycled materials and uses them to rebuild brand new, structurally flawless internal machinery. This fasting-induced autophagic reset serves as a powerful shield against cardiac aging, directly clearing out the debris that leads to myocardial stiffness, reducing chronic oxidative stress, and actively rejuvenating the contractile strength of your heart. However, this profound recycling process operates on a strict and delicate biological spectrum, and it can become dangerous if pushed past a critical physiological threshold. While brief, controlled bursts of fasting-induced autophagy act as a highly therapeutic restoration project, an overly prolonged or excessively aggressive fast can cause this cleanup mechanism to lose its selective control. If your body is deprived of nutrients for too long, or if fasting is paired with a severe long-term caloric deficit, the continuous activation of AMPK and the total suppression of mTOR can cause the autophagic machinery to run completely wild. Instead of carefully consuming only damaged debris, the heart cells enter a state of panic and begin to frantically degrade their own healthy, essential structural proteins, functional enzymes, and contractile fibers simply to secure a desperate supply of survival amino acids. This state of uninhibited overactivation can lead to autophagic cell death and a progressive, dangerous loss of total heart muscle mass, a condition clinically recognized as cardiac atrophy. As the muscular walls of your heart thin out and lose their structural density, the heart's overall stroke volume, the actual amount of blood it can forcefully eject with each individual contraction, declines significantly. The heart becomes structurally weakened, less elastic, and increasingly incapable of generating the robust blood pressure required during physical exertion or stress. This delivers a vital clinical warning. A well-managed fast can beautifully clean your heart's internal machinery, but an excessive, unmonitored fast can cause your heart to literally cannibalize its own structural foundation. The cardiovascular effects of intermittent fasting extend far beyond the muscular walls of the heart itself, exerting a powerful and transformative influence on the vast network of blood vessels that form your circulatory highway. The absolute master regulator of your vascular health and arterial elasticity is the endothelium. This is a single, highly delicate layer of specialized cells that lines the entire interior surface of your blood vessels, acting as an active interface between your flowing blood and the rest of your arterial walls. The primary marker of a healthy, resilient endothelium is its constant ability to synthesize and release a vital gaseous signaling molecule known as nitric oxide. This molecule diffuses directly into the surrounding smooth muscles of your arteries, commanding them to relax, loosen, and widen. During a structured fast, the rising levels of the ketone beta-hydroxybutyrate act as a potent chemical messenger that talks directly to your genetics. Ketones function as natural inhibitors of restrictive proteins that normally keep your DNA wound up tightly. By blocking these restrictive proteins, ketones open up specific genetic pathways within your endothelial cells, leading to a dramatic upregulation of the gene responsible for endothelial nitric oxide synthase. This is the exact enzyme tasked with creating nitric oxide from passing amino acids. The resulting surge of nitric oxide within your arterial walls induces a state of systemic relaxation throughout your vascular system. As your blood vessels widen and lose their baseline stiffness, the hydrostatic pressure exerted against their walls drops significantly, leading to a clinically measurable reduction in both your systolic and diastolic blood pressure. This vascular relaxation provides immense mechanical relief to the heart, drastically reducing its afterload, which is the structural resistance the left ventricle must push against to eject blood to the rest of your body. In addition to improving blood pressure dynamics, fasting initiates a profound defensive cascade against the underlying drivers of atherosclerosis, which is the progressive hardening and narrowing of the arteries caused by fatty plaques. Atherosclerosis is fundamentally a chronic, low-grade inflammatory disease where cholesterol particles become trapped and oxidized inside the subendothelial space, triggering an aggressive and inappropriate immune response. Intermittent fasting directly dampens this vascular inflammation by silencing a complex intracellular protein structure called the NLRP3 inflammasome. By putting this inflammatory master switch to sleep, fasting halts the continuous recruitment of aggressive immune cells into your existing arterial plaques. This prevents them from turning into volatile foam cells that secrete destructive enzymes that digest the protective collagen caps covering those plaques. As a direct result, fasting helps stabilize vulnerable arterial plaques, significantly reducing the catastrophic risk of a plaque rupture, which is the primary proximal cause of sudden heart attacks and strokes. However, these incredible vascular benefits must be carefully balanced against the simultaneous risks introduced by acute fluid shifts and changes in blood thickness. As your insulin levels drop during a fast, your kidneys rapidly flush out massive amounts of sodium and water. If you do not aggressively counter this fluid loss with precise water and electrolyte replacement, you can quickly enter a state of severe intravascular dehydration. This rapid fluid loss causes a significant contraction of your total blood plasma volume, leading to a clinical state known as hemoconcentration. Because the fluid component of your blood has been drained away, the relative concentration of red blood cells, platelets, and large clotting proteins like fibrinogen increases dramatically, making your blood significantly thicker, stickier, and more viscous. Thicker blood drastically alters the fluid dynamics inside your arteries, creating an intense frictional drag force against the delicate vessel walls, which is known as endothelial shear stress. In individuals who already possess brittle, advanced, or calcified arterial plaques, this sudden increase in blood thickness and frictional stress can create a highly volatile environment. The physical force of the thick blood dragging across a fragile plaque can cause it to tear or erode. Once the interior of the plaque is exposed to this sticky, platelet-rich blood, it can trigger an instantaneous and massive clotting cascade that blocks coronary blood flow entirely. This highlights a sobering clinical paradox. While the anti-inflammatory nature of fasting works long-term to heal your blood vessels, the acute dehydration of an unmanaged fast can thin the line between a stable artery and a sudden, catastrophic vascular event. The final and most critical dimension of the fasting heart involves its complex relationship with the autonomic nervous system, which is the master neurological control center that dictates your resting heart rate, contraction speed, and internal electrical pathways. Your autonomic nervous system constantly balances the accelerator pedal of the sympathetic nervous system, which drives your fight-or-flight response, with the braking pedal of the parasympathetic nervous system, which controls your rest and digest functions via the long vagus nerve. Intermittent fasting exerts a fascinating two-phase influence on this delicate neurological balance. During the initial 12 to 20 hours of a fast, your brain detects the temporary absence of incoming food and initiates a mild adaptive stress response. This triggers a localized surge of stress hormones like norepinephrine, which increases your alertness and sharpens your focus so you have the drive to seek out nutrients. However, as your body transitions into a deep and stable state of ketosis, a profound neurological shift occurs. Your brain significantly upregulates parasympathetic tone, sending powerful soothing signals down your vagus nerve directly to the heart's natural pacemaker. The vagus nerve releases a chemical called acetylcholine, which binds to the pacemaker cells and slows down their electrical firing rate. This leads to a lower resting heart rate and a significant increase in heart rate variability, which is the premier clinical marker of a resilient, stress-protected cardiovascular system. Hot on the heels of this calm electrical equilibrium, a sudden disruption can occur if your fast induces critical imbalances in your serum electrolytes. The seamless, rhythmic electrical beat of your heart is entirely dependent on the precise maintenance of chemical concentration gradients across your heart cell membranes. These gradients create the electrical action potentials that cause the heart to contract as a synchronized unit. The absolute cornerstones of this electrical stability are two vital minerals, potassium and magnesium. As your insulin levels drop during a fast, your kidneys rapidly flush out massive amounts of sodium and water. If you fail to replace these minerals, your serum levels will drop, introducing a state of severe cellular instability. A drop in potassium alters the electrical properties of your heart cells, making it take much longer for them to reset their electrical charge after every single beat, a dangerous state visible on an electrocardiogram as a prolonged QT interval. Simultaneously, a deficiency in magnesium paralyzes the microscopic pumps responsible for maintaining ion balances, leaving the heart cell membranes highly irritable, unstable, and prone to spontaneous, inappropriate electrical misfires. When a delayed electrical reset caused by low potassium combines with the intense cellular irritability caused by low magnesium, it creates a lethal environment for dangerous heart rhythms. This electrical instability is further amplified by the sudden spikes in adrenaline that occur during periods of poor fasting-induced sleep or intense physical stress. If a single premature or ectopic heartbeat occurs during the vulnerable reset phase of an unstabilized, mineral-depleted heart, it can trigger a catastrophic electrical short circuit known as ventricular fibrillation. During ventricular fibrillation, the coordinated pumping contractions of your heart dissolve instantly into a useless, chaotic, trembling motion. Your systemic blood pressure drops to zero immediately. Blood flow to the brain stops entirely, and sudden cardiac death can occur within minutes. This harsh clinical reality underscores the absolute necessity of medical awareness and meticulous electrolyte management. While fasting has the unique power to optimize your heart's neurological resilience, ignoring the basic, unyielding chemistry of your minerals can turn a health-conscious fast into a sudden, silent, and fatal cardiac event.